fold reduction in solubility with temperature when you solidify aluminum. So here's the melting point of pure aluminum. Here's the solubility. This is a log scale over here. So I've got like 0.6 cubic centimeters of hydrogen per 100 grams of aluminum. Sort of like they did in steel, in terms of it's basically a number you get out of the measurement, but it's not an atomic percent or anything. But you go from like 50 down to less than 0.05. Okay, so that's about 100 in that case, right? Yeah. But a tremendous drop in solubility, and it comes out just like the CO2 coming out of the Sprite. In this case, it's solidification. It comes out while you're solidifying. It gets pushed ahead, and it ends up as porosity. Aluminum castings or aluminum welds always have some porosity. And the question is how much. And there's an ASTM spec, what is it? ASTM A143 or something. It's just, I could have brought it. It's the reference radiographs, and it costs like $1,300 now. It used to cost $300. Fortunately, I bought mine in the 1990s before these societies decided to make big profits on things. But it actually has a bunch of radiographs from real welds that they have created as standards, and you can look at aluminum of this thickness, and there's a radiograph, and it will have 1 through 8. And 8 is the one with lots of porosity, and 1 is the one with very little porosity. There is no example in there that you can specify 0 porosity. You always get a little bit of porosity. Okay? And a lot of people say, well, I don't want any porosity. Well, good for you. Okay? I want an infinite bank account. But even if I'm Bill Gates, I don't have an infinite bank account. Okay? There's a limit to my bank account. There's a limit to how low the porosity can go. You can't get rid of all the porosity. Well, does it really matter? And the answer is no. Not in most cases, unless you might specify for a motorcycle part or a critical application, and motorcycles are critical applications, a level 1 or 2 porosity, which is just a couple of little pores. Level 2 might be 2 or 3 1 millimeter or smaller pores per square inch of your X-ray. Okay? Whereas level 8 might be 50 pores per square inch. In any case, this is data on the strength of aluminum alloys. This is 7039 versus porosity, and this is porosity going out to 40%. I mean, this is worse than Swiss cheese. Okay, and I lost from 50 ksi tensile strength down to, I lose about 40%. My strength loss is proportional to the amount of void space. So if I got a couple of little pores in there, who cares? Okay? I had a case once where a guy fell out of a tree stand. I've actually had a number of cases where people fall out of a tree stand. But this one was an cast aluminum turnbuckle. Okay? I think this was a homemade tree stand or something. Anyway. And they took a picture, they took an x-ray of it, and there were like 4 or 5 little pores, and I mean little pores, like less than half a millimeter in this whole, little turnbuckle. And I remember it was White Plains, New York, and I was on the witness stand, and I was trying to explain how little this porosity was. And I think I'd ripped my piece of paper and shown them, a brittle material. And aluminum's not that brittle a material. It's a ductile material, particularly this type of casting that it was made out of. And I said, turns out the witness box had a little table that was about 4 feet by 3 feet. That was my little table in front of my chair. I said, it'd be the equivalent of having 5 ping pong balls on the table. Okay? And it was. I'd done the calculation, the porosity in the area of the little turnbuckle. So the reason the turnbuckle broke was not anything defective about the turnbuckle. It's because if you overload things, they sometimes break. The guy had been climbing improperly. In any case, so the strength goes down, the elongation goes down faster, so you lose ductility, but you still have 10 oh, this is 10, this does, oh, here's the ductility. I thought it was on here. Elongation over here, you go from 15% to 5%. So you've lost 2/3, or actually you've lost more than you've lost 70% of your elongation, but you still got some elongation. It's not a brittle material. It's not shattering because of porosity. It just loses strength proportional to the volume of the porosity. It loses stretch somewhat faster, but it's not defective. In most cases, we're talking about welds that have less than 1 or 2% porosity, so it's within the scatter band of the strength. Okay? The natural variation you're going to get in the material. So it's not that big a deal, but people get all worked up when they see porosity. Oh, it's a defect. Well, it's an imperfection, but it really is not going to limit the life of your structure. One of the problems with aluminum, another problem in welding of aluminum, is crater cracking. So when you finish making a weld on aluminum, you're welding along, you don't just stop and pull the electrode off. Okay, because you do, the aluminum shrinks 6% on solidification. What you should do as a welder, your welding technique is you're running along, and as you get to the end, you backtrack, and you allow the backtracking to fill more metal in there so that your final cross section of your weld pool is not one that is concave. Okay, so I'm looking cross section wise where I have a concave weld pool and it will result in solidification cracking. I want to have something where I fill that up so that the final part of the weld looks like this, and I get good solidification and push all that alloying element up to the top and don't get a liquation crater crack. So crater cracks are a common problem, and it all has to do with welder technique, and that's why the same guy who welds steel is not necessarily qualified to weld aluminum. Most of these guys figure, I can weld steel, I can weld aluminum, I can weld titanium, I can weld zirconium, I can weld anything. Well, maybe not. Okay, there are techniques with each material. Okay, another problem with aluminum is it tends to form an oxide. And you got to clean off that oxide. That aluminum oxide is what gives aluminum its corrosion protection, gives it high temperature oxidation resistance, which we use in many alloys like the nickel alloys and stuff. We add aluminum to give it oxidation resistance at high temperature and stuff. You have to clean the oxide off the aluminum if you're going to weld well. Aluminum oxide melts at 2000 degrees centigrade. Aluminum melts at 660 degrees centigrade. And if you've ever welded aluminum, or maybe if you looked at aluminum welds and they haven't cleaned the oxide, it looks like it's got a skin on it. Because it does. It has an aluminum oxide skin. And to weld aluminum well, you have to clean it well. And most steel shipyards, you could not do a good job of welding aluminum. You got a lot of grease and other things around, you'll get porosity, you'll be out of spec, even if it's not really a problem. You have to be cleaner. You have to do good housekeeping when you're welding aluminum. And you also have to take the aluminum and you have to clean off the oxide. You can clean it off by grinding, but that's expensive. What a lot of people do for parts is they'll put them through a chemical bath cleaning, and the chemical bath cleaning could be sodium hydroxide at 150 degrees Fahrenheit. Okay, so you soak it in hot sulfuric oxide, or sodium hydroxide. You can use sulfur chromic oxide or phosphoric acid and chromic acid. What's the problem with these two? Anybody know what the problem with these two that contain chromic oxide is? Environmental. CrO3. That's Erin Brockovich. That's what she got all that money for those kids who were having liver cancer and all these other birth defects and things in California. Chromic acid is a carcinogen. It's one of the most potent carcinogens we know. And the reason you didn't have chrome bumpers after 1982 or so on automobiles in the United States, between 1982 and about 1995, no more chrome bumpers. Why? Because the people in the chrome plating shops, they did a study and showed that they had a much higher incidence of cancer. Okay? So they shut down the shops. It wasn't until the mid-90s that Ford built an environmentally protected sulfuric acid, chromic acid plating shop for Ford Explorers. Cost them a couple $100 million with all the controls, but you know, no one's going to be breathing chromic acid fumes in a modern electroplating shop. But it took them about 15 years to design the controls and stuff so that we now are back to doing chromium plating. Hey, when I was a student back here in that little lab across from my office, when we cleaned glassware, we did this in high school too, but we didn't have quite as big a thing, but there was a sink in there, and they had a tank of chromic acid about this big, and whenever you cleaned your glassware, you would then, after it was clean and you would rinse all the soap off and everything else, you would take some tongs and you would dip it in the bath of black chromic oxide, and you would rinse it off in that because chromic oxide sort of etches the glass super clean, okay? And then you put it under the water and you just run the chromic oxide down the sink, okay? Down the drain. If I did that today, they'd probably handcuff me and take me away, okay? But this was the 1970s, early 70s. 10 years later, you know, Aaron Brockovich kind of learned about chromic acid, or hexavalent chrome is what other people call it. This is hexavalent chrome. Look at it, CrO3. 2 times 3 is 6. That's hexavalent. So we don't use these so much anymore. Okay, sulfuric acid, you can use hot sulfuric acid, fairly concentrated, or ferrous sulfate. Anyway, so you have to have cleaning tanks. Now the problem with cleaning tanks is maintaining them. Okay, I had a problem, actually it was down at Quincy Shipyard in the probably late 1970s, maybe early 80s. But they were, did I mention this problem before to you? They were making some barges. We don't have our Coast Guard here, but they were making some barges that was going to carry number 6 bunker oil. I thought I mentioned this to you. Okay, and the rinse tank had a pH of 2.3. The rinse water had a pH of 2.3. That's as strong as Coca-Cola, you know, in terms of acidity. And then, so they had cracking problems. Okay, before we go with ambers, I think I have time to give you a case study, and so on Monday we'll start titanium and probably finish up with titanium. So this is something, a guy that is the engineer for a family-owned business out in Oklahoma, sends me an email this past January. I'd done some work with him on, he basically does weld repair on aluminum cast engine blocks for aviation. So if you got a Lycoming or a Teledyne Continental engine and your aluminum case that has your crankshaft and the piston heads bolt to this crankcase. The crankcase is just sort of there to keep the oil in the sump. To you know, you've got oil running through the holes in the crankcase for the bearings, then it comes spraying out. And the crankcase, or the engine, it's not really an engine block. It doesn't. The pistons are inside these piston heads that are made out of aluminum, but they're all hot isostatic pressed and stuff. But it's just basically a shroud. The case that he's welding is just a shroud to kind of contain the oil that's spraying out of the crankshaft as it's running around and stuff, and the connecting rods and stuff. So it turns out this type of weld repair used to be done by Lycoming and TCM, but they kind of gave it up, and there's only a couple of places that the FAA has approved, and every now and then someone will have a failure and they'll send it, and in this case they sent it off to the Canadians. It was a Canadian failure, and the Canadians were criticizing them because they did a hardness check across the weld zone, and then they did a chemistry check, and even though the alloy is Aluminum Association 355 casting alloy, which is an aerospace materials specification of 4280, the recommended filler is 4145, and I showed you the table of recommended fillers. So if you go look that up, actually I should have it somewhere here. Nope, it's got to be, where did I put it? It's right here. So if I look at a table, this is the same table I showed you before, and if I'm at 355 casting and I'm going to weld it, to 355 casting, I should use 4145. And if I look at the 3 footnotes here, it will tell me 4145 will give me the maximum strength. Okay? And if I read the other footnotes, it will say 4047 may be used for some applications, 4043 may be used for some applications. Okay? So anyway, this engineer at this company that's repairing engines says, well, we ran a little test. And actually, this is his email to me down here. And he basically says, we ran a little test, and if you flip it over, the test shows that they put these steel studs into this casting so that you can bolt the 2 halves of the engine together. If you just put the stud in the base material of the 355 casting and you torque it, you'll get, or you measure the hardness, you'll get a Brinell hardness of 93, and he did it 2, as he says. They did a test, but it was a small sample size. Pretty small sample size, 2. Okay, they did 2 tests to find out what would happen. And it turns out the stud into 4043 weld is torqued to the same level in their test. Stud with a helicoil. Everybody know what a helicoil is? Anybody know what a helicoil is? It's a little steel spring shaped thing that if you screw up the threads in something, you can over thread it. You can drill it out, over thread it, put this little diamond shaped spring in there and create new threads, okay, of the original size. Sometimes people put specify helicoils for the original manufacturer because you have steel into aluminum, and steel into steel helicoil is actually a little bit better, and so you can get a bigger thread of steel helicoil into aluminum and have more bearing area and stuff, but they're a little pricey. But anyway, and here's a double helicoil. Anyway, they did some tests, and they got some. They were supposed to get 204 inch-pounds, and they got plenty of this in most cases, and they did it in the 4145 weld. And he writes me this email, and he says, well, Tom, what do you think? Should we be using 4145 so that we've been using 4043, which the handbook says you can use 4043, but 4043 has a lower hardness, and it has a slightly lower strength than the base metal 355. So it's under matching, and so they'd have a failure, and people would go in and analyze it, and even though that wasn't the cause of the failure, they would criticize them because this thing was under matching, and under matching is generally considered bad. Okay, well, so I looked. He asked me the question, so I looked up the different alloys that the welding handbook said you could use, and you can match the composition almost exactly with a 408 or 409 or 410 electrode of the 355 if you compare it to the 355 alloy. The 4043 is a little lower in alloy content than the 409, which is why it doesn't have as much strength. Okay, the 4145 is much higher in alloy content and will give you better strength. So you could have matching composition and maybe matching strength, under matching, or over matching. And the question he's asking is, we've been doing this for 30 years, and we learned how to do it from the engine manufacturer, and we're one of the only certified people in the country to do this. What should we be using? So I write back and I say, well, just like when you ask me a question, there's no simple answer. I can't say yes or no. Okay? Okay. I say, what do you do? I said, well, and I've just explained that one of them's under matching, one's over matching, one's. I said the technical answer is that 4145 gives you the strongest, but in his application, static strength is not really controlling. I mean, this thing is nowhere near loaded to its strength capacity. It's just there to keep the oil in. There's no real load on it in service. Okay, there's no pressure inside, no pressure differential. All the crankshaft and piston loads are somewhere else, basically. You just have to put some studs in it so you can bolt things on, and there's lots of area. So yeah, 4145 is the strongest. It's more highly alloyed. You have experience with 4043, and it's hard to suggest changing from a proven performer. I mean, why change something, if it's not broke, don't why fix it? 409 is match composition, and 410 and 411 are very close. They probably give intermediate strength. So you can have low strength that you're being criticized for, overmatching, which you might actually make things worse in terms of creating a stress concentration at the higher strength, because this is quite a bit higher strength. Or you can match the composition, and so people may not even know you made a weld, okay, if they're not really careful. So what would I do? Given the fact that people criticize you, even if they don't have any data, for using undermatching 44.3, I'd go with 4009. Why do you need overmatching? You don't need overmatching in this case. You're not looking for strength. If you go for something that matches the composition, probably not very much. It's probably not any more difficult to weld. 4145 with higher alloy might be a little more difficult to weld. So the real answer is I was not going to make a design decision for him. I gave him his options and let him make the decision. Because let's face it, if an aircraft goes down and people start criticizing, I don't want them coming back to me and say, oh, you designed this, in this email to him, right? So I have to protect myself. Okay, so Amber, is it working? Okay, you want to come tell us about what you're going to tell us about? And we'll finish up on Monday. I'll do titanium on Monday. You can turn the camera off.